Imagine this traveller drifting between thoughts drawn here as if the cosmos itself guided your steps. What are the odds that an object from another star could arrive looking so simple, yet behave like something that rewrites the rules of nature? A fragment of another world shedding carbon dioxide at a rate no comet its size should survive. A silent visitor threading a 1 in 20,000 path between Mars and the Sun. A light that blinked once and was gone. A whisper hidden in the background of our understanding. You're here now, observer. Listen before you fall asleep beneath the stars. On July 1st, 2025, the Atlas survey station in Chile detected what initially appeared to be a faint, unremarkable smudge against the background stars. Automated detection software flagged the object as another moving point of light similar to thousands of minor bodies previously catalogued. However, follow-up calculations quickly revealed that this was no ordinary solar system comet or asteroid. Instead, its orbital parameters indicated a hyperbolic trajectory, a path with an eccentricity far greater than 1. In orbital mechanics, this is the defining signature of an interstellar object, a visitor not gravitationally bound to the Sun, and therefore incapable of ever returning. The object was formally designated C225N1 Atlas, and later classified as 3I Atlas, marking it as only the third confirmed interstellar object in human history. Its discovery immediately drew scientific interest for one simple reason: objects on hyperbolic trajectories carry information from beyond our own planetary system, effectively functioning as natural probes from distant stellar environments. One of the first notable features of 3I Atlas was its extraordinary velocity. Travelling at approximately 130,000 miles per hour, 209,000 km/h, it was moving significantly faster than typical comets originating from the Oort cloud. Such velocity implied that the object did not originate from within our solar system, but had been wandering through interstellar space for an extended period, possibly millions of years, before crossing into the Sun's gravitational sphere of influence. Initial observations using the Gemini North Telescope in Hawaii revealed an unexpected characteristic active sublimation. As sunlight warmed the object, it began to produce a visible coma, a cloud of gas and dust surrounding an unresolved nucleus. This contradicted the assumption that long-travelled interstellar fragments would be chemically and thermally inert, due to extensive radiation exposure and extreme cold. The presence of a coma suggested that volatile materials had been preserved on or beneath the surface despite prolonged exposure to interstellar conditions. The emergence of this coma also raised questions about the object's composition and structure. Traditional models of cometary physics assume that ices such as water carbon dioxide and carbon monoxide sublimate in predictable ways depending on distance from the Sun. However, early spectroscopic data indicated that 3I Atlas was dominated by carbon-bearing volatiles in unusual proportions, potentially hinting at a formation environment unlike that of typical solar system comets. Another point of interest lay in the object's trajectory through the inner solar system. 3I Atlas followed a path that brought it within approximately 1.188 astronomical units of Earth, a safe but observationally advantageous distance. Its closest approach to the Sun perihelion was scheduled for October 29, 2025, between the orbits of Earth and Mars. Although Earth would be positioned on the opposite side of the Sun during this event, making direct observation impossible, the pre-perihelion and post-perihelion windows offered valuable opportunities for data collection. As the object became brighter and more active, major observatories redirected their instruments toward it. The Hubble Space Telescope, the James Webb Space Telescope, JWST, the Swift Observatory, and ground-based facilities across several continents coordinated to track changes in its coma, analyze its composition, and refine its orbital parameters. Despite these efforts, every new dataset seemed to generate more questions than answers. The object's activity levels, thermal behavior, and chemical signatures consistently fell outside established models. This pattern of anomalies highlighted a broader scientific theme. Interstellar objects may exhibit a diversity far exceeding previous expectations. Before 2017, no interstellar visitor had ever been observed. The discovery of Wasam Oumuamua, followed by 2I Borisov in 2019. and now 3I Atlas has revealed that such objects vary dramatically in morphology, chemistry and behaviour. 3I Atlas, with its active sublimation and unusual volatile ratios, may represent yet another category within this growing taxonomy. By late July and early August, as more detailed images became available, it became evident that 3I Atlas would not yield simple answers. The coma expanded steadily. Brightness fluctuated in ways that resisted easy interpretation. And most importantly, the nucleus remained unresolved, preventing direct measurement of its size or rotational characteristics. The inability to observe the solid core directly complicated efforts to model the object's physical structure. This lack of clarity did not signify scientific failure, but rather the inherent challenge of studying small distant bodies moving at extreme velocities. Even with high-precision telescopes and coordinated international support, interstellar objects remain difficult subjects. Their rapid transit through the inner solar system provides only a narrow observational window, and they often remain surrounded by their own outgassed material obscuring internal features. In sum, the discovery of 3I Atlas represents a significant milestone in astronomy. Not only does it offer a rare opportunity to study material from beyond the solar system, but it also challenges existing theoretical frameworks. Its active coma, unusual chemical profile and hyperbolic trajectory invite scientists to reconsider assumptions about how planetary systems form and evolve elsewhere in the galaxy. The object stands as a reminder that our understanding of interstellar matter is still in its infancy, and that each new detection expands the boundaries of what we consider possible. As research continues, the scientific community remains aware that the object will soon recede into the outer darkness, beyond the reach of even our most powerful instruments. The data collected during this brief encounter will therefore shape our understanding not only of 3I Atlas, but of interstellar visitors as a whole, laying the foundation for future discoveries in the decades ahead. The trajectory of 3I Atlas through the inner solar system provides a clear framework for understanding both its motion and the unique observational challenges it presents. Unlike periodic comets whose elliptical orbits allow repeated visits and predictable geometry, 3I Atlas follows a hyperbolic escape path entering the solar system once before, returning irrevocably to interstellar space. This single passage is governed entirely by gravitational mechanics that have been unfolding for millions of years long before its detection by terrestrial telescopes. To conceptualize its path, the solar system can be imagined as a large orderly clockwork with the planets tracing predictable long-term orbits around the Sun. Into this stable arrangement, 3I Atlas enters not as a participant but as an external influence, an object whose kinetic history and formation lie elsewhere. Its motion resembles a high-velocity projectile passing through the gears of a finely engineered machine. Despite the complexity of the surrounding environment, the interstellar visitor threads through the system with precision, determined by its inbound velocity vector and the Sun's gravitational influence. A critical point in this trajectory is the perihelion, the closest approach to the Sun, scheduled for October 29, 2025. Unlike many comets whose perihelia lie beyond the orbit of Earth, 3I Atlas passes between the orbits of Earth and Mars at a distance of approximately 130 million miles, roughly 1.4 astronomical units from the Sun. At this distance, solar heating becomes intense enough to drive significant sublimation, increasing the object's activity and expanding its surrounding coma. However, the geometry is particularly unfavourable for observation during the perihelion window. Earth will be positioned on the opposite side of the Sun, rendering the object invisible to all Earth-based and near-Earth telescopes due to solar glare. This period, known as solar conjunction, is a major limitation in the scientific study of 3I Atlas. For nearly 2 months from late September through early November, astronomers will be unable to collect meaningful data. The timing is especially significant, as perihelion is when comets typically exhibit their most dramatic physical and chemical changes, alterations driven by peak solar heating. Missing this phase means that researchers must infer key aspects of the object's behaviour indirectly, and rely on pre- and post-conjunction observations to reconstruct its evolution. Before conjunction occurs, however, 3I Atlas offers a unique opportunity. On October 3, 2025, it will make a close approach to Mars, passing within approximately 29 million kilometers of the planet. This is closer than the distance between Mars and its outer moon Deimos. As a result, spacecraft currently orbiting Mars, most notably the Mars Reconnaissance Orbiter MRO, equipped with the high-resolution HiRISE camera, could in principle observe the interstellar visitor during a period when Earth cannot. Although the resolution achievable from Mars orbit will not match that of Hubble or the James Webb Space Telescope, such data could provide valuable insights into the coma, morphology or dust-tail structure during the critical perihelion phase. After emerging from conjunction in early December 3rd, Atlas will reappear in Earth's pre-dawn sky, initially in the constellation Virgo and gradually shifting toward Leo. By this time, however, the object will be moving rapidly away from the Sun at velocities estimated to exceed 150,000 miles per hour, 241,000 km/h. As it recedes into the outer solar system, its brightness will diminish significantly, and the coma and tail, if present, will gradually dissipate. Observational opportunities during this period will therefore be limited by both decreasing luminosity and increasing distance. The overall brightness of 3I Atlas is another important factor. Even at its most illuminated state, the object is expected to reach only magnitude 11 or 12, making it visible exclusively through telescopes and entirely invisible to the unaided eye. This distinguishes it from high-profile comets such as Hale-Bopp or Neowise, whose dramatic tails captured public attention. Instead, 3I Atlas remains a scientifically interesting but visually modest visitor, one requiring sensitive instruments and coordinated international observation strategies. Further analysis of the object's trajectory reveals additional clues about its origin and long-term history. Its calculated incoming speed of approximately 25 photoseconds relative to the local standard of rest suggests that it did not originate from a recently perturbed star system, but rather has been travelling through interstellar space for millions of years. The trajectory places it among the dynamical class of objects associated with the Milky Way's thick disk population, older stars formed early in the galaxy's history. These stars and the planetary systems that might have coalesced around them possess different chemical compositions compared to younger systems like our own, potentially explaining the unusual chemistry observed in 3I Atlas. Another important aspect of the visitor's journey concerns future planetary encounters. In March 2026, months after leaving the inner solar system, 3I Atlas will pass relatively near Jupiter. This distant encounter has prompted speculation about whether NASA's Juno spacecraft currently orbiting the gas giant could be redirected to observe the object. Although such a mission would require precise timing and navigational adjustments, it represents a potentially valuable opportunity for close-range data collection. Overall, the path of 3I Atlas through the solar system highlights both the opportunities and limitations inherent in studying interstellar objects. Its rapid movement and brief visibility impose strict observational constraints, while the geometry of its approach creates windows of time in which certain instruments can gather critical data. At the same time, the diversity of perspectives from Earth, Mars, and potentially Jupiter offers a multifaceted look at a phenomenon that was until recently purely theoretical. As 3I Atlas continues its passage through our neighbourhood, it serves as a reminder of the dynamic nature of the solar system and the broader galactic environment. Objects from other star systems are not merely hypothetical. They are active participants in a complex gravitational landscape that spans light years. Studying their trajectories provides not only scientific insights, but a deeper appreciation of the interconnectedness of stellar systems across the Milky Way. The first high-quality observations of 3I Atlas came on July 21, 2025, when the Hubble Space Telescope HST was directed toward the interstellar visitor. These observations provided the earliest detailed view of the object's morphology and established a foundation for all subsequent studies. As with many small bodies observed at great distances, the images did not reveal a resolved nucleus. Instead, what emerged was a combination of point source brightness and a surrounding halo of diffuse light information that, while limited, carried substantial implications for understanding the object's physical state. The initial Hubble image presented an object with a compact teardrop-shaped coma glowing softly against the stellar background. This morphology is consistent with active sublimation, in which volatile ices transition directly from solid to gas as solar radiation increases. The shape was not symmetrical. The coma showed a subtle elongation directed away from the sun, suggesting the presence of an antisolar tail, although early observations could not confirm this structure definitively. The geometry of the coma, combined with the object's increasing brightness, indicated that the nucleus was actively shedding material behavior consistent with solar heating, but particularly interesting for an object believed to have spent millions of years in interstellar space. From a technical standpoint, Hubble's point spread function allowed astronomers to set an upper limit on the nucleus size. The unresolved point source implied a diameter no greater than approximately 3.5 miles, 5.6 kilomeson. In practice, the nucleus could be significantly smaller. Without resolved imaging, the measurement reflects an upper bound rather than a direct determination. Nonetheless, the apparent brightness of the object suggested a nucleus that was either highly reflective, unusually active, or both. A striking feature of the Hubble image was the appearance of the background stars. Because the telescope tracked 3 Atlas, directly keeping the object perfectly centered in the field, the stars in the background appeared as streaks. This effect occurs because Hubble's tracking system follows the motion of the target across the sky, causing the stationary stars to blur into elongated trails during the exposure. The resulting images not only confirmed the object's motion, but created a visually distinctive representation of the dynamics at play, a fast-moving interstellar body gliding through a static stellar background. The coma's structure carried additional information about the underlying physics. As the object crossed inward from approximately 4 astronomical units, the intensity of solar radiation increased sufficiently to activate the sublimation of water ice, though, as later data would show, the object's composition appeared to involve far more carbon dioxide than water. The dust and gas released during this process formed a roughly spherical envelope around the nucleus, but its asymmetric shape indicated that non-gravitational forces, solar radiation pressure and temperature gradients, were already influencing the developing coma. One early puzzle emerged from the absence of a clearly defined tail. In typical comets, dust and ion tails become increasingly visible as they approach the Sun. Yet in the case of 3I Atlas, the expected anti-solar tail was faint enough to be nearly undetectable. Hubble's initial data suggested a directional bias in the coma, but not a pronounced tail consistent with standard comet behavior. This ambiguity persisted until late August, when deeper imaging from Gemini South confirmed the existence of a faint, elongated structure extending away from the Sun. The tail did exist, but its visibility depended strongly on viewing geometry and the sensitivity limits of the observing instrument. Another key parameter measured by Hubble was the dust production rate. Based on the brightness and spread of the coma, the object appeared to be producing dust at levels comparable to moderately active comets, originating from the Oort cloud. Despite having travelled through interstellar space for extended periods, this observation challenged expectations. Exposure to cosmic radiation over millions of years would be expected to alter or deplete volatile ices. Yet 3 Atlas behaved as though much of its volatile content had been preserved. This resilience implies either efficient shielding mechanisms, an unexpectedly large reservoir of volatile materials beneath the surface, or formation conditions that produce volatiles capable of long-term survival. Hubble's inability to resolve surface features or rotation state further added to the mystery. While nuclei of this size ordinarily exhibit periodic brightness, variations caused by rotation, 3I Atlas showed no detectable modulation within the sensitivity limits of the observations. Several explanations remain plausible: a very slow rotation period, a nearly pole on orientation relative to Earth, or a surface of uniform reflectivity. Each scenario carries distinct implications for structural composition and dynamical history. Another intriguing result from Hubble's imaging involved non-uniformities within the coma. Several brightness gradients and density variations suggested the presence of localized jets or active regions on the nucleus. These anisotropies could indicate spatial variations in volatile distribution or structural features that preferentially release gas along specific vectors. However, without direct imaging of the nucleus, these interpretations remain provisional. By late August, additional telescopes provided complementary perspectives, but Hubble's early work established essential baselines. It confirmed active sublimation, constrained nucleus size, hinted at complex dust behaviour, and documented the unconventional coma structure. Together, these data reinforced the notion that 3I Atlas was not simply a scaled version of the interstellar comet 2I Borisov, nor did it resemble the inert, tumbling behaviour of 1 Oumuamua. Instead, it represented a third distinct example, underscoring the chemical and physical diversity of interstellar objects. Ultimately, Hubble's observations demonstrated that even at early stages of its solar approach, 3I Atlas was already deviating from canonical cometary behaviour in ways that required new theoretical frameworks. It possessed a small, unresolved nucleus, an unexpectedly active coma, a subtle and delayed tail development, and potential internal structural complexities. These findings established the foundation for the more advanced spectroscopic and dynamical studies that would follow, shaping the scientific narrative of one of the most intriguing interstellar visitors yet observed. The chemical composition of 3I Atlas quickly emerged as one of the most significant and unexpected aspects of the interstellar visitor. When the James Webb Space Telescope JWST captured its first spectroscopic data on August 6, 2025, the results challenged every established model of cometary chemistry. Unlike typical solar system comets, where water vapour dominates sublimation products, 3I Atlas exhibited a carbon dioxide to water ratio of roughly 8:1. This single measurement positioned it as a chemical outlier among all known cometary bodies. Under standard comet formation, theories water is expected to be the most abundant volatile released when a comet approaches a star regardless of its place of origin. Even comets considered water poor rarely exceed a CO2-H2O ratio of 2:1. In contrast, the extreme ratio observed in 3I Atlas suggested either an atypical formation zone or a fundamentally different evolutionary history. This discrepancy represented one of the earliest indications that the object could not be fully explained through familiar solar system analogues. The complexity deepened with follow-up observations from Sphere-X, the spectrophotometer for the history of the universe, epoch of Ryanization and ICES Explorer, conducted between August 8th and 12th. Sphere-X revealed that the carbon dioxide emission was not confined to a region near the nucleus, but instead extended outward to a radius of at least 348,000 kilometers. To contextualize this scale, the CO2 coma was significantly larger than the Earth-Moon distance. No previously observed comet, interstellar or otherwise, had exhibited a carbon dioxide cloud of this magnitude. This extended CO2 halo posed fundamental questions about outgassing dynamics. A nucleus estimated to be no more than a few kilometers in diameter cannot easily account for such a large and diffuse emission region through typical sublimation processes alone. Either the surface area actively releasing CO2 was dramatically larger than expected, or the gas was interacting with the surrounding environment in ways not yet fully understood. Possibilities include fragmentation of volatile rich material, distributed sources of sublimation within the coma, or enhanced ionization, and solar wind interactions expanding the gas cloud far beyond classical predictions. The spectral profile of 3I Atlas grew even more puzzling when instruments sought evidence of water vapour. Early data from the Swift Observatory had detected hydroxyl OH radicals in the vicinity of the object products typically formed when solar ultraviolet radiation dissociates water molecules. This initially suggested substantial water content. However, Sphere-X subsequently identified only weak or non-detectable water emission lines, placing strong upper limits on H2O production rates. The discrepancy between OH detection and water signatures implied a more complicated underlying chemistry than simple sublimation. One explanation emerged from the detection of solid phase water. Sphere-X identified absorption features at 1.5 and 2.1 micrometers wavelengths, consistent with the spectral fingerprints of water ice rather than vapour. This finding implied that water was indeed present on or near the surface, but was not sublimating efficiently. Instead, it remained bound in the solid phase even as CO2 escaped readily. Such behaviour could result from a surface mantle, a crust of organic or carbon-rich material, formed during the object's long exposure to interstellar radiation. This insulating layer could suppress H2O sublimation, while permitting CO2, which sublimates at lower temperatures, to escape through fractures or thin regions. The comparison with previous interstellar visitors underscores the uniqueness of 3I Atlas. The second confirmed interstellar object, 2I Borisov, displayed enhanced carbon monoxide CO but not carbon dioxide. The first, 1I Oumuamua, showed no detectable gaseous emission at all. Together, the three objects span a wide chemical spectrum, suggesting that interstellar debris is far more diverse than expected. The distinct chemical signature of 3I Atlas implies that it formed in a region where carbon dioxide ice was abundant relative to water, a characteristic consistent with specific temperature and pressure conditions in certain protoplanetary environments. Such a formation environment likely lies near the CO2 snowline in an alien protoplanetary disk. This region represents a narrow thermal corridor where water remains in vapor form, but carbon dioxide condenses directly into ice. Objects forming within this zone would naturally accumulate CO2-rich material, while incorporating relatively little water. These chemical conditions differ from the dominant volatile profiles observed in comets, originating in our own solar system, which form either inside the water snowline where volatiles are scarce, or far outside it, where water dominates. An alternate explanation centers on the effects of cosmic radiation during interstellar transit. High-energy particles can break apart complex molecules, modify ices, and produce secondary compounds through radiolysis. Over millions of years, such processes could reduce water content, enhance CO2 production, or reshape the chemical landscape of an icy nucleus. The reddish spectral slope observed by Sphere X aligns with surfaces altered by prolonged radiation exposure, providing further support for this hypothesis. Another possibility is that the extended CO2 coma results from fragmentation processes. Rather than being a single monolithic nucleus, 3I Atlas could be composed of multiple loosely bound fragments, each releasing CO2 independently. As these fragments drift apart, they would create a distributed source of gas capable of sustaining a large emission region. However, Hubble images have not yet identified clear evidence of discrete subcomponents, making this explanation plausible, but not confirmed. Finally, temperature-dependent sublimation behavior may account for some of the observed chemical ratios. At distances of 2.25 to 3.5 AU from the Sun, the early phase of observation water sublimation is inefficient, while CO2 sublimation remains vigorous. If 3I Atlas contains water that becomes active only at higher temperatures, the CO2 dominance may diminish after perihelion. Post-perihelion monitoring will therefore play a crucial role in determining whether the chemical imbalance is intrinsic or merely a consequence of temperature regimes encountered during approach. In summary, the chemistry of 3I Atlas represents an unprecedented case study in the diversity of planetary formation processes across the galaxy. Its extreme CO2 abundance limited water vapor emission, and enormous extended coma challenge conventional models, and highlight the limitations of extrapolating solar system comet behavior to interstellar bodies. Whether these traits reflect its formation environment, its interstellar processing history, or ongoing fragmentation dynamics remains an open question, one that the remainder of the observation campaign aims to address. 3 months after its discovery, 3I Atlas remains one of the least understood objects ever observed entering the solar system. While multiple observatories, including Hubble, JWST, Swift Sphere X, and numerous ground-based telescopes have collected substantial data, the most fundamental characteristics of this interstellar visitor remain unresolved. The result is a paradox. Although scientists know more about 3I Atlas than about any previous interstellar object, during comparably early observation phases, the data have simultaneously introduced new layers of uncertainty. One of the most pressing unknowns concerns the size of the nucleus. Hubble's imaging constraints place the diameter somewhere between 320 meters and 5.6 kilometers, a range so large that it offers limited practical insight. This uncertainty arises because the nucleus is completely hidden within its coma, making direct imaging impossible. Without a clear resolution of the solid core, multiple interpretations remain viable. The nucleus could be compact and reflective, producing strong luminosity from a small surface area. Alternatively, it could be larger but darker, emitting similar brightness due to a combination of sublimation activity and scattering in the coma. This inability to directly resolve the core underscores the inherent difficulty of studying distant dust-enshrouded bodies. A related challenge is determining the rotation state of 3I Atlas. Cometary nuclei typically exhibit periodic brightness changes caused by rotation which alters their cross-sectional area or exposes different active regions to solar radiation. However, the photometric record for 3I Atlas shows no such brightness periodicity. Several hypotheses have been proposed the object may be rotating extremely slowly, presenting a nearly pole on orientation relative to Earth, or possessing unusually uniform surface properties that mask rotational signatures. Each scenario has distinct implications. A slow rotation could indicate internal damping or structural cohesion. A pole on orientation would affect tail morphology and gas flow. Uniform surface reflectivity might reflect unique compositional traits or dust redistribution patterns. Another major gap in understanding concerns the presence and behaviour of water. Early ultraviolet observations from the Swift Observatory detected hydroxyl radicals, a common indicator of water sublimation. Yet subsequent observations from Spherex found water emission lines to be extremely weak or absent. The detection of solid phase water ice complicates this picture further. The conflicting signals suggest that water may exist beneath an insulating crust that inhibits sublimation, or that the conditions for water vapour production have not yet been met during the early approach to the Sun. This discrepancy represents a key chemical mystery, as water signatures often provide critical clues about formation and activity processes. The dust tail, an important diagnostic feature in cometary science, also remains poorly understood. Although Gemini South eventually confirmed a faint anti-solar tail in late August, its initial absence was unexpected. A subtle or delayed tail could imply several possibilities: unusually large dust grains that resist radiation pressure, a low dust-to-gas ratio, or a viewing geometry that compresses the observable tail into a narrow angular profile. If large grains dominate, this would be consistent with a nucleus that produces material through sublimation of denser ices like CO2 rather than water. One of the most intriguing uncertainties concerns activity patterns within the coma. Hubble's early images suggested that a portion of the material appeared to flow in a sunward direction, counterintuitive in classical cometary physics, where most dust and gas are pushed away from the Sun. While geometrical projection effects may explain this anomaly, the possibility remains that 3 Atlas exhibits non-standard gas flow behaviour or unusual structural features that influence outgassing directionality. Such patterns, if confirmed, would warrant significant revisions to existing models of cometary fluid dynamics. The composition beyond CO2 and H2O remains largely unknown. While Webb and Spherex have characterized major volatiles trace species such as organic molecules, sulfur-bearing compounds and noble gases, have not yet been conclusively identified. These chemical constituents would provide valuable information about the formation, temperature, radiation exposure, and environment of the progenitor system. However, detecting them requires higher sensitivity and longer integration times, both of which are constrained by the rapidly narrowing observation window. Another major challenge is the unobservability of perihelion. Because 3I Atlas will be located behind the Sun relative to Earth, during its closest approach, scientists will miss the most thermally intense and chemically active phase of the object's trajectory. This period is typically when comets undergo substantial structural change fragmentation, or dramatic increases in outgassing. The inability to directly study these processes introduces significant uncertainty. Researchers will have to infer perihelion behaviour through post-perihelion signatures which may be incomplete or ambiguous. Tracking the object's trajectory also presents unresolved complications. While its interstellar origin is beyond dispute, the exact path it has followed across the galaxy remains a subject of estimation rather than certainty. Over millions of years, gravitational interactions with stars' molecular clouds and the galactic potential will have altered its course. Pinpointing a precise origin requires data of a precision that is unlikely to be obtained in the available timeframe. The best current models suggest an origin in the galactic thick disk, but this remains provisional. Another significant unknown relates to the driving mechanism behind the extended CO2 coma. Conventional sublimation from a compact nucleus is insufficient to explain the scale of the gas halo. Whether this arises from fragmenting material chemical layering within the nucleus distributed sublimation or interactions with the solar wind remains unresolved. Each potential mechanism carries implications for the structure and stability of the object. Finally, the question of non-gravitational acceleration remains open. While 3I Atlas has shown no measurable deviation from gravity-dominated motion to date, such deviations often emerge only after perihelion, as increased heating intensifies outgassing forces. If anomalous accelerations similar to those of 1 Oumuamua appear, they would significantly reshape interpretations of the object's nature. Conversely, the absence of such forces would reinforce conventional cometry models, albeit with unusual chemical traits. In summary, despite unprecedented early observation efforts, many basic characteristics of 3I Atlas remain unknown. The limited observational window, unresolved nucleus, inconsistent water signatures, unusual chromodynamics, and incomplete chemical profile collectively highlight the complexity of studying interstellar objects. These uncertainties underscore the broader challenge of extrapolating solar system comet behaviour to bodies formed under entirely different stellar conditions. The coming months, particularly the post-perihelion phase, may provide crucial insights, but the possibility remains that 3I Atlas will depart the solar system with many of its most fundamental properties still unresolved. The classification of an object as interstellar relies on specific quantitative criteria rooted in orbital mechanics, rather than on unusual chemistry or unexpected physical behaviour. For astronomers, the key determinant is whether the object is gravitationally bound to the Sun. If it is not, if it enters the solar system on a path that guarantees it will never return, its origin must lie beyond our star's influence. This is the case for 3I Atlas, whose trajectory and velocity provide conclusive evidence of an interstellar origin. The first indicator is orbital eccentricity. Objects in the solar system follow elliptical orbits with eccentricities less than 1. A value of exactly 1 corresponds to a parabolic trajectory, the theoretical boundary between bound and unbound motion. Any value greater than 1 signifies a hyperbolic orbit, an open path that allows the object to escape the Sun's gravity permanently. With an eccentricity of roughly 1.7, 3I Atlas lies deep within the hyperbolic regime. Such a value cannot be produced by typical gravitational interactions with planets, which may slightly perturb cometary orbits, but cannot impart the necessary velocity to create a strongly hyperbolic path. A second, more definitive metric is the asymptotic velocity v, representing the speed the object would possess at an infinite distance from the Sun. Solar system bodies, even long-period comets, have v values that approach 0. In contrast, 3I Atlas has a v near 25 km, far too high to result from perturbations within the Sun's gravitational domain. This measurement effectively proves that the object originated outside the solar system, having entered with a velocity imparted by processes occurring around another star. The rarity of such objects is not due to their absence in the galaxy, but to the difficulty of detecting them. Wide-field surveys like those conducted by the Atlas system image the entire visible sky every 2 days, yet in nearly a decade of observations, Atlas has identified only this one interstellar visitor. Coupled with the discoveries of 1 Oumuamua in 2017 and 2 the Borisov in 2019, these detections suggest that interstellar objects pass through the solar system more often than we realise, but most remain too faint, too small or too fast-moving to detect with current technology. Once an unusual trajectory is identified, confirmation becomes a collaborative process. Observatories worldwide collect astrometric measurements to refine the orbit, and only when multiple analyses agree that the object's motion is hyperbolic and its v is significantly positive does the International Astronomical Union assign it the I designation. This stringent process ensures that only objects truly originating from beyond the Sun's gravitational influence receive the interstellar classification. The naming system reflects both sequence and rarity. Dersky Oumuamua, 2 Borisov, and now 3I Atlas. Despite sharing the same classification, these objects display profound differences in morphology, chemistry, and behaviour. Oumuamua showed no detectable gas emission and exhibited non-gravitational acceleration. Borisov behaved like a classical comet, but with unusually high carbon monoxide levels. 3I Atlas, with its extreme carbon dioxide dominance and extended gas coma, represents yet another category. Together they illustrate the diversity of small bodies formed in other planetary systems. The confirmation of an interstellar object holds significant value for planetary science. These bodies serve as natural samples from other protoplanetary disks, offering insights into chemical compositions, temperature gradients, and formation mechanisms beyond those available within the solar system. Since interstellar travel remains currently out of reach for spacecraft, these natural visitors are the only physical materials from other star systems available for study. The future promises more opportunities. When the Vera C. Rubin Observatory begins full operations, its legacy survey of space and time will be capable of detecting many more interstellar objects. Models predict anywhere from 1 to 70 per year depending on their true abundance. Such discoveries would allow scientists to move beyond individual case studies and build statistical models of interstellar debris populations. For now, 3I Atlas stands as the latest confirmation that the solar system is not isolated but part of a dynamic galactic environment. Its hyperbolic orbit, high inbound velocity, and unusual chemistry provide irrefutable evidence of an origin beyond the Sun, and highlight both the scientific challenges and opportunities that arise when material from distant stars briefly enters our observational reach. The arrival of 3I Atlas prompted immediate comparisons with the two interstellar visitors that came before it, Oumuamua in 2017 and 2AM Borisov in 2019. Together, these three objects have revealed a surprising truth. Interstellar debris is not a uniform class of material, but a collection of bodies with remarkably different properties, origins, and behaviours. The contrast among them has become one of the most compelling aspects of modern planetary science. The first known interstellar object, Oumuamua, displayed characteristics unlike any comet or asteroid observed within the solar system. It showed no detectable coma or tail despite passing relatively close to the Sun. Its elongated shape and tumbling motion were inferred from its highly variable light curve, suggesting an object stretched perhaps 10 times longer than it was wide. Most unexpectedly, Oumuamua exhibited a small but measurable non-gravitational acceleration as it exited the solar system. This force resembled the kind produced by cometary outgassing, yet no gas or dust was ever detected. Proposed explanations include sublimation of difficult-to-detect volatiles such as hydrogen radiation pressure, acting on an unusually thin object, and other mechanisms that remain debated. Whatever the cause, Oumuamua challenged the assumption that interstellar visitors would behave similarly to known categories of small solar system bodies. The second visitor, 2I Borisov, was far more familiar in appearance. Discovered in August 2019, it immediately displayed the characteristics of an active comet, a bright coma, a well-developed tail, and sustained outgassing as it approached the Sun. However, even Borisov diverged from solar system norms. Spectroscopic measurements revealed exceptionally high levels of carbon monoxide, far exceeding the COH2O ratios typical of comets in our system. This chemical signature suggested formation in an unusually cold region of its parent protoplanetary disk, colder than most zones where solar system comets originated. Borisov therefore represented an interstellar analogue to cometary activity, but one whose chemistry reflected a markedly different environmental history. Against this backdrop, 3I Atlas introduces a third distinct profile. Unlike Oumuamua, it shows clear signs of active sublimation. Unlike Borisov, the dominant volatile driving its activity is carbon dioxide, not water or carbon monoxide. The extreme CO2 abundance distinguishes it from both prior visitors and from nearly all known solar system comets. The morphology of its coma adds to this uniqueness, compact, bright, and initially showing only a faint, hard-to-detect tail. The delayed identification of the antisolar tail, which required deep imaging from Gemini South, stands in contrast to Borisov's dramatic and immediate tail development. These differences indicate a mode of activity governed by distinct physical and chemical processes. The three visitors also differ significantly in nucleus morphology and size constraints. Oumuamua's elongated shape and rapid tumbling were inferred from brightness variations, because it remained point-like in all images. Borisov appeared roughly spherical, with a nucleus estimated at several hundred meters across. For 3I Atlas, the nucleus remains unresolved, but Hubble's upper size limit of approximately 5.6 kilometers contrasts sharply with the smaller estimated dimensions of the other two. The possible range for 3 Atlas's nucleus spans over an order of magnitude, leaving open the possibility of either a relatively large, moderately reflective body or a smaller object exhibiting unusually strong coma-driven brightness. The behavioural differences among the three objects further emphasise their diversity. Oumuamua's acceleration remains one of the most enigmatic findings in contemporary astronomy, while Borisov followed gravitational predictions with precision. 3I Atlas, at least during its pre-perihelion phase, also shows no measurable non-gravitational acceleration, though this may change as it approaches or exits perihelion. Each object reveals a different relationship between radiation sublimation and internal structure. These distinctions carry broader implications for exoplanetary science. If 3 interstellar objects discovered within a span of less than a decade display such disparate chemistries and behaviours, the underlying population must be remarkably varied. Planetary formation processes across the galaxy appear capable of producing a wide spectrum of volatile compositions, structural properties, and dynamical histories. Oumuamua may represent a dehydrated fragment processed by cosmic radiation Borisov, a pristine ice-rich body from a cold outer disk, and 3I Atlas, a carbon dioxide-dominated object formed near a CO2 condensation zone in an alien planet-forming environment. This diversity also highlights the limitations of using solar system comets as universal templates. Prior to 2017, our understanding of cometary physics was shaped almost entirely by observations of objects originating within the Sun's gravitational domain. The 3 interstellar visitors demonstrate that such assumptions do not necessarily apply elsewhere. Planetary systems with different stellar masses, disk temperatures, metallicities, and evolutionary histories may produce small bodies with fundamentally different chemical and physical characteristics. Finally, the diversity among the 3 objects illustrates the importance of observational geometry and detection bias. Oumuamua was observed only after its perihelion passage, when most of its activity, if it had any, would have subsided. Borisov was detected earlier in its inbound trajectory, enabling months of preparation and observation. 3I Atlas was discovered at an ideal distance for planning, but will be hidden behind the Sun during the most critical period of its activity. These constraints affect how much of each object's behaviour can be studied, and limit the conclusions scientists can draw about them as representatives of a broader population. Taken together, the 3 known interstellar visitors reveal 3 distinct personalities: an inert accelerating enigma, a familiar but chemically unusual comet, and now a carbon dioxide-dominated active body with unprecedented coma characteristics. Their differences suggest that the Milky Way is filled with a vast and chemically diverse population of planetary fragments, each carrying unique information about the environments in which they formed. As more interstellar objects are discovered in the coming years, the emerging picture is likely to become even more complex, illustrating the wide range of conditions under which planetary systems across the galaxy evolve. The dynamical behaviour of 3I Atlas presents a series of unresolved questions that highlight the limits of current cometary physics and underscore how interstellar objects can deviate from familiar patterns. While much attention has focused on chemistry and morphology, the object's motion, both gravitational and potentially non-gravitational, holds crucial clues about its internal structure and the mechanisms driving its activity. The first interstellar visitor, 1I Oumuamua, established a precedent for dynamical anomalies. As it exited the solar system, astronomers detected a small but statistically significant acceleration that could not be explained solely by gravity. The effect was consistent with forces produced by cometary outgassing, yet no gas or dust was observable. This prompted numerous hypotheses ranging from sublimation of hydrogen ice to radiation pressure acting on an unusually reflective or low-density object. Regardless of the explanation, the existence of this non-gravitational acceleration demonstrated that interstellar visitors might not conform to the dynamical behaviour seen in solar system bodies. Against this background, 3I Atlas, as observed so far, appears dynamically ordinary. Its trajectory conforms closely to the predictions of gravitational models with no deviations beyond current measurement uncertainties. However, this apparent normality may be temporary. Non-gravitational forces arising from sublimation or structural evolution typically become most apparent near or after perihelion, when solar heating is strongest, and outgassing can produce measurable momentum changes. Because 3I Atlas will be unobservable during its perihelion passage, any acceleration that develops during that window might only become detectable afterward, as astronomers compare pre- and post-perihelion orbital elements. The chemistry of the object complicates this assessment. Unlike Oumuamua, whose hypothesized hydrogen outgassing would be extremely difficult to detect, 3I Atlas emits large amounts of carbon dioxide, a heavier molecule capable of exerting measurable dynamical effects. If the object begins to accelerate due to directed CO2 jets or enhanced sublimation, the resultant forces could be more easily observed. Thus, post-perihelion tracking will play an essential role in determining whether 3I Atlas exhibits any dynamical anomalies similar to those of its predecessor. The coma morphology contributes further complexity. Early Hubble observations suggested that some material appeared to flow toward the Sun, an unexpected outcome since sublimated gas and dust typically accelerate away from the Sun under the influence of radiation pressure. This apparent sunward elongation is likely the result of projection effects. Three-dimensional outgassing patterns compressed into a two-dimensional image plane can create misleading visual impressions. However, until higher resolution multi-angle observations become available, the true flow structure cannot be definitively characterized. A more significant puzzle lies in the scale of the extended carbon dioxide coma. The enormous size of the CO2 cloud implies gas production rates, or transport mechanisms, far exceeding those typical of comets with nuclei only a few kilometers across. One hypothesis suggests that 3 Atlas may not be a monolithic body, but rather a loose aggregate of smaller fragments that collectively contribute to the observed gas output. However, Hubble's imaging does not show signs of fragmentation, such as multiple brightness peaks or elongated shapes. Alternatively, interactions between CO2 ions and solar wind magnetic fields may accelerate gas to high velocities, inflating the coma to observed dimensions. If correct, this would indicate that electromagnetic processes play a more significant role in shaping interstellar objects than previously assumed. The rotation state of 3I Atlas also remains unresolved. Most small bodies experience torques from asymmetric outgassing, often producing detectable changes in rotational period or inducing tumbling motions. Despite evidence of strong activity, 3I Atlas shows no clear brightness modulation indicative of rotation. Several explanations remain plausible. The object might rotate slowly. It may be oriented with its rotational pole directed toward Earth. Or its surface may be sufficiently uniform that rotation does not produce observable variation. Without constraints on rotation, modelling outgassing jets and dynamical evolution becomes substantially more difficult. Observations from the Transiting Exoplanet Survey satellite TESS offer a further point of interest. Preliminary data hinted at possible activity from 3I Atlas at distances where most comets remain inert. If validated, this could indicate the presence of highly volatile ices or sublimation mechanisms independent of direct solar heating. Early activation would influence both the coma structure and the dynamical forces acting on the object, potentially affecting its orbit in ways that may only become detectable after perihelion. Together, these uncertainties illustrate why the dynamics of 3I Atlas remain an open problem. While its motion currently appears consistent with gravitational expectations, the combination of extreme carbon dioxide activity possible, early outgassing, poorly constrained rotation, and complex gas flows all introduce the possibility of future deviations. Post-perihelion astrometric tracking will therefore be critical, offering perhaps the only opportunity to detect subtle accelerations that could reveal internal structure composition gradients or jet-driven torques. Ultimately, the dynamical behavior of 3I Atlas represents an ongoing test of our ability to model small bodies formed under conditions vastly different from those of the solar system. Whether it continues to follow predictable gravitational motion or begins to exhibit anomalous acceleration, its trajectory will deepen our understanding of how interstellar objects evolve when exposed to the sun's environment. As observations continue, the object's movement through space may prove as informative as its chemistry, providing a complementary window into the physics of these rare galactic travelers. The discovery of 3I Atlas initiated one of the most extensive and coordinated astronomical monitoring efforts ever assembled for a small body entering the solar system. Because interstellar objects are both rare and transient, the scientific community mobilized, quickly integrating data from space-based observatories, ground-based telescopes and planetary missions to construct a comprehensive observational campaign. This global collaboration reflects not only the scientific value of 3I Atlas, but also the recognition that the opportunity to study such an object is limited and will never repeat. NASA's Science Mission Directorate led the coordination, establishing a multi-mission strategy that leveraged the strengths of its major observatories. The Hubble Space Telescope HST provided high-resolution imaging capable of constraining coma morphology dust distribution and upper limits on nucleus size. The James Webb Space Telescope JWST conducted infrared spectroscopy identifying volatile species and mapping emission lines with unprecedented sensitivity. Swift, with its ultraviolet capabilities, monitored photochemical processes affecting molecules such as hydroxyl radicals. Meanwhile, Sphere-X captured wide-field infrared data critical for mapping the unexpectedly large carbon dioxide coma that surrounds 3I Atlas. Each instrument contributed a distinct layer of information, and together they formed a multi-wavelength dataset more comprehensive than any previously assembled for an interstellar object. Ground-based facilities also played a central role. Telescopes in both hemispheres, Gemini North in Hawaii and Gemini South in Chile, provided timely images that helped confirm features initially suggested by Hubble. The Gemini South deep imaging campaign was particularly important as it finally revealed the faint anti-solar dust tail that earlier observations struggled to detect. The Paloma Observatory contributed photometry and astrometry, refining brightness curves and trajectory predictions. Smaller observatories worldwide participated in coordinated monitoring runs, filling temporal gaps left by larger facilities and enabling continuous tracking during the early phase of the object's approach. The observational timeline is dominated by the challenge posed by solar conjunction. As 3I Atlas approaches perihelion on October 29, 2025, its proximity to the Sun in the sky will render it effectively unobservable from Earth for nearly 2 months. This blackout period coincides with the moment when the object's activity is expected to reach its maximum. During perihelion, solar heating should drive the strongest outgassing increased dust production, and possibly trigger structural changes such as fragmentation. Because Earth-based and near-Earth observatories cannot view the object, during this time the scientific community will miss the most dynamically informative phase of its evolution. To compensate for this observational gap, researchers have explored the potential contributions of spacecraft located elsewhere in the solar system. The Mars Reconnaissance Orbiter MRO offers a unique opportunity because 3I Atlas will pass within roughly 29 million kilometers of Mars on October 3, 2025, just days before Earth begins losing sight of the object. MRO's high-rise camera is capable of high-resolution imaging, albeit at distances far greater than typical targets. Even so, any images obtained during this window could provide valuable information about coma evolution during a period inaccessible from Earth. Spacecraft farther from the Sun are also being considered. NASA's Psyche mission will pass within 0.3 AU of 3 Atlas in September 2025, and preliminary assessments suggest it may be able to obtain opportunistic observations. ESA's JUICE spacecraft en route to Jupiter could potentially observe the object during its November approach, depending on pointing constraints and operational priorities. There have even been discussions about whether the OSIRIS APEX mission, tasked with studying asteroid Apophis, might contribute late 2025 data. Although none of these spacecraft were designed for cometary science, their instrumentation could still capture scientifically useful data if geometry and timing permit. The radio astronomy community has also contributed to the global campaign. Facilities such as the Green Bank Telescope and the Deep Space Network have monitored 3I Atlas for potential radio emissions associated with charged particles, plasma interactions, or unusual electromagnetic behaviour. While no anomalous signals have been reported, these observations provide important constraints on the object's physical, environment, and activity. Coordination among observatories, agencies, and scientific teams has been facilitated by rapid communication channels, including the International Astronomical Union's Minor Planet Center, the Astronomers' Telegram Network, and dedicated interagency communication groups. Observation requests that would normally require long scheduling horizons have been expedited to accommodate the unique demands of monitoring an interstellar object. In several cases, time on major telescopes has been reallocated or granted on short notice, a rare exception to standard proposal cycles. This collective effort serves not only scientific goals but also broader applications. The techniques developed for tracking 3I Atlas, high-cadence astrometry, rapid spectroscopic response, and flexible telescope scheduling are directly relevant to planetary defense. Although 3I Atlas poses no danger to Earth, the methodologies used to monitor it closely parallel the procedures that would be required for tracking potentially hazardous near-Earth objects. As perihelion approaches, the intensity of observation continues to increase. Researchers are preparing for the brief but crucial post-conjunction window when 3I Atlas will reappear in the pre-dawn sky of early December. At that point, the object will be receding from the Sun at high velocity, rapidly becoming fainter as it moves toward the outer solar system. Despite these challenges, the scientific community aims to extract maximal information during this final window, particularly regarding changes in chemistry, brightness, nucleus activity, and potential non-gravitational acceleration. Taken together, the global observation campaign surrounding 3I Atlas reflects the scientific significance of studying a rare interstellar visitor. It demonstrates the astronomical community's ability to mobilize, rapidly coordinate across continents, and integrate diverse observational assets. The data collected during this period will form the most detailed record of an interstellar object, to date offering insights that will shape our understanding of planetary formation and interstellar chemistry for decades to come. The idea of sending a spacecraft to intercept 3I Atlas is naturally appealing. A close-range encounter could provide data that no telescope on or near Earth could achieve: direct imaging of the nucleus in situ measurements of gas and dust, and potentially even isotopic sampling of material from another star system. Yet when examined through the constraints of orbital mechanics, propulsion capabilities, and mission timelines, the concept becomes far more challenging than intuition suggests. The fundamental obstacle is velocity. By the time 3I Atlas was discovered, it was already moving at more than 200,000 km per hour relative to the Sun. This translates to a hyperbolic excess velocity at speed after escaping the Sun's gravity of roughly 25 km per second. To intercept an object moving this fast, a spacecraft must not only match its speed, but also align with its trajectory, a requirement that drastically increases the energy demands of the mission. Current chemical propulsion systems cannot produce the necessary delta V, which would exceed that of even the most powerful rockets by an order of magnitude. Even a mission launched immediately upon discovery would face severe limitations. Interstellar objects spend only a short time within observational reach. By the time an interceptor could be designed, constructed, and launched processes that take years under normal aerospace procedures, 3I Atlas would already be far beyond the inner solar system, moving into a region where solar power is weak, communication delays are long, and travel times become prohibitive. These practical constraints define the core challenge: our detection timelines and propulsion capabilities are not yet compatible with rapid response intercept missions for fast-moving interstellar objects. Nevertheless, the scientific community has examined whether existing spacecraft already in flight might offer unexpected opportunities. NASA's Psyche mission will pass within approximately 0.3 AU of 3I Atlas in September 2025. Although Psyche's instruments were not designed for cometry observations, its cameras and spectrometers could theoretically acquire useful data during a distant flyby, provided the spacecraft can be oriented appropriately and mission priorities allow for such observations. The geometry remains difficult, but the possibility demonstrates how opportunistic science can complement planned objectives. ESA's JUICE spacecraft presents a similar opportunity. Bound for the Jovian system, JUICE will cross a region of space from which 3I Atlas might be observable in early November 2025, during the period when Earth-based telescopes are blocked by solar conjunction. While the spacecraft's pointing constraints and operational schedule impose strict limits, even a small contribution could fill part of the observational gap during perihelion. Some proposals have pushed the concept further, exploring whether the Juno spacecraft currently orbiting Jupiter could be redirected toward an intercept. These assessments involve complex trajectory analysis in which Jupiter's gravity would serve as a slingshot to redirect Juno onto a path converging with 3I Atlas in March 2026. While the calculations suggest a theoretical possibility, several practical barriers exist. Juno's remaining fuel, its mission commitments, its aging systems, and the need for institutional approval. Redirecting an active mission requires balancing scientific opportunity against mission risk and operational feasibility. Other missions, such as OSIRIS-APEX, have appeared in discussions as potential contributors, though their trajectories and operational constraints make meaningful observations uncertain. OSIRIS-APEX is designed for close proximity asteroid science and carries instruments well suited for surface analysis, but aligning its flight path with the hyperbolic trajectory of 3I Atlas remains unlikely. Given these constraints, long-term planning has turned toward dedicated missions capable of responding rapidly to future discoveries. ESA's Comet Interceptor, scheduled for launch in 2029, embodies this forward-looking approach. The mission will place a spacecraft at the Sun-Earth L2 point, allowing it to wait in a ready state for years. Once a suitable target, such as a newly discovered interstellar object, appears, Comet Interceptor can initiate a fast transfer trajectory, capitalizing on its pre-positioned location, to avoid the delays associated with traditional mission preparation. This strategy reflects lessons learned from Vuamnd, Oumuamua to Usgat Borisov, and now 3I Atlas. The observational window for interstellar objects is too short for ad hoc mission design. Theoretical research into propulsion technologies continues to explore options for future intercept missions. Concepts involving solar sails' nuclear thermal propulsion and advanced electric propulsion have been modelled as potential solutions capable of achieving the required delta V for intercepting fast-moving interstellar objects. These approaches remain developmental, but the interest reflects a growing recognition that interstellar visitors represent unparalleled scientific opportunities. Their chemistry structure and isotopic composition can reveal formation conditions in environments fundamentally different from our own. Although direct interception of 3I Atlas is beyond current capability, the effort to explore these possibilities has produced valuable insights. It highlights the mismatch between discovery timelines and spacecraft readiness, underscores the importance of pre-positioned missions, and demonstrates the scientific motivation for developing faster and more flexible propulsion systems. Interstellar objects will continue to pass through the solar system, each offering a rare sample from another planetary system. Preparing to study them up close requires advances not only in astronomy, but also in aerospace engineering mission architecture and interagency coordination. In this context, 3I Atlas serves as both a scientific target and a catalyst for future innovation. Its passage illustrates the limits of our present technology, while shaping the strategies we will use to confront similar opportunities in the decades ahead. The scientific desire to approach it directly may not be achievable now, but it is already influencing the missions that will meet the next interstellar visitor with greater readiness. One of the most striking features of 3I Atlas is its unusual chemical composition, particularly the dominance of carbon dioxide relative to water, whereas most comets in the solar system exhibit strong water emission. As they approach the Sun, 3I Atlas displays an inverted ratio with carbon dioxide emerging as the primary volatile species. Understanding this anomaly requires examining several natural mechanisms that could produce such a chemical profile. Each explanation remains grounded in known physics and laboratory evidence, though the available data are not yet sufficient to determine which mechanism is most responsible. A plausible explanation begins with the role of snowlines in protoplanetary disks. In any forming planetary system, temperature gradients determine where various volatiles condense from gas into ice. Water condenses at relatively low temperatures far from the central star, while carbon dioxide condenses at somewhat higher temperatures closer to the star. If 3I Atlas formed in a region inside the water snowline but outside the carbon dioxide snowline, it could accumulate large quantities of carbon dioxide ice while remaining relatively depleted in water. The environment would resemble a zone analogous to the inner regions of our own asteroid belt, warm enough to prevent widespread water ice condensation, yet cool enough to allow carbon dioxide to freeze out. In this scenario, 3 Atlas's chemistry would reflect the local thermodynamic conditions during its formation, rather than any exotic process. A second explanation involves radiation processing during the object's long interstellar journey. Over millions of years, exposure to cosmic rays and ultraviolet photons can significantly alter the chemistry of icy surfaces. High-energy particles can break apart water molecules, drive complex reaction pathways, and convert organic material into simpler carbon-bearing species such as carbon dioxide. Laboratory simulations of cosmic ray processing show that water ice can be selectively destroyed or chemically transformed under continuous irradiation, while carbon dioxide is more resistant to degradation. If 3I Atlas spent an extended period in interstellar space, these processes may have reshaped its surface composition, increasing its carbon dioxide abundance relative to water. The reddish spectral coloration detected on its surface aligns with this possibility, as radiation-processed ices often exhibit similar signatures. A third explanation centers on physical structure. Comets that spend long periods in interstellar or distant solar environments can develop insulating crusts composed of dust, organics, and radiation-altered materials. Such crusts a few centimeters to several tens of centimeters thick can inhibit the escape of water vapor because water sublimates only efficiently when heat penetrates deeply into the ice. Carbon dioxide, however, sublimates at lower temperatures and may escape through cracks, pores, or thinner regions of the surface. This selective permeability could produce exactly the pattern observed in 3I Atlas. Robust carbon dioxide emission with weak or undetectable water vapor signatures despite the likely presence of water ice beneath the crust. Observations from SphereX, which identified features consistent with solid water ice, support the idea that water may be present but not dynamically active. Another hypothesis relates to structural fragmentation. Instead of a single cohesive nucleus, 3I Atlas may consist of multiple loosely bound carbon dioxide-rich fragments. If solar heating causes these fragments to gradually separate, each fragment could sublimate, independently producing a distributed carbon dioxide coma far larger than what a single nucleus could generate. This fragmentation-driven outgassing could explain the unusually extended carbon dioxide cloud, which spans hundreds of thousands of kilometers. At the same time, if the fragments are coated with insulating material or contain relatively little water, the weak water vapor signatures would be consistent with this structural model. Fragmentation would also help explain the stability of the comet's overall brightness, despite high levels of activity, as distributed sublimation can smooth out variations that would otherwise arise from localized jets. Thermodynamics alone may provide a simpler explanation. At the heliocentric distances at which 3 Atlas has been observed, water sublimation is inefficient due to low surface temperatures. Carbon dioxide, however, remains highly volatile at these distances. Models of volatile sublimation predict that comets dominated by carbon dioxide ice should exhibit strong activity at several astronomical units from the Sun, while water-rich comets typically activate closer to the Sun. If 3I Atlas is simply entering a region where carbon dioxide sublimation dominates the observed chemistry, could reflect the expected temperature dependence of volatile release, rather than an intrinsically unusual composition. In this view, water vapor may increase significantly after perihelion when the object experiences peak thermal input, though the upcoming solar conjunction will obscure direct observation of that phase. Grain size effects also offer clues. The subtle and faint tail of 3I Atlas suggests either large dust grains or dust with atypical optical properties. Carbon dioxide-driven sublimation tends to release fewer fine particles than water-driven sublimation. Laboratory studies show that carbon dioxide ice can lift aggregates of unusual composition and size distribution, which could affect the morphology of the coma and tail. This subtle morphology aligns with the idea that the dominant volatile controls the physical behaviour of dust and gas in the surrounding coma. Collectively, these explanations demonstrate that the carbon dioxide dominance of 3I Atlas is not inherently anomalous in a physical sense. Each mechanism formation, environment, radiation, processing, insulating crusts, structural fragmentation, temperature dependence and grain size effects has precedent in laboratory data, theoretical models or observations of solar system comets. The difficulty lies not in identifying plausible explanations, but in determining which combination best describes this particular interstellar object. The overlapping nature of these mechanisms means that several could be acting simultaneously, reinforcing one another in ways that complicate interpretation. As further observations become possible after the object emerges from solar conjunction, the evolution of the volatile ratios will help differentiate these hypotheses. Increasing water emission would support thermodynamic or crust-breaking explanations. Continued dominance of carbon dioxide might indicate a genuinely water-poor composition or efficient shielding of subsurface ices. Until then, the chemical signature of 3I Atlas remains an open question framed not by the absence of explanations, but by the abundance of them. Although 3I Atlas has been examined through every available instrument and analytical framework, the object ultimately represents more than a collection of measurements, uncertainties, and evolving hypotheses. It is a reminder of how limited our sample of interstellar material remains, and how easily a single visitor can expose gaps in long-standing assumptions about planetary formation, volatile chemistry, and dynamical evolution. The object's trajectory, composition, and behaviour all reinforce the same underlying lesson. The space between stars contains a diversity of processes and histories that our models are only beginning to approximate, whether future observations clarify its nature or leave it partly unresolved. Atlas demonstrates the importance of remaining open to evidence that does not conform neatly to expectations. It underscores how scientific progress often emerges not from definitive answers, but from carefully confronting the questions that resist resolution. Traveller. As we drift out of this long orbit of thought, the mystery of 3I Atlas lingers like a faint echo in the dark. We have followed its path across millions of miles, examined the light it sheds and the silence it keeps, and still it slips past our understanding with the quiet confidence of something older than our questions. Some visitors arrive in our sky only once, but their traces remain shaping how we think about the universe and our place inside it. Tonight we learned more facts, more numbers, more trajectories, yet somehow we walk away knowing that the heart of the mystery remains untouched, as if the cosmos keeps certain truths folded behind a veil of starlight. And that is all right, observer. Not every answer is meant to be held. Some are meant to remind us how much wonder still exists. Thank you for sharing this quiet journey. In a universe so vast, the simple act of looking upward, of listening to the dark, is an extraordinary thing. You're small, yes, but never insignificant. Every question you carry becomes part of the long conversation between humanity and the stars. If this story found you tonight, you're welcome to stay for the next. Rest well, traveller, stay curious. The universe will keep watch.